So liquids, solids, and IMFs. That's what we're going to be focusing on now. The first thing I want to talk about is what we have been talking about up to this point was all types of bonding. And bonding is intramolecular forces. Intra means within. So when we're talking about intramolecular forces, that's what we've been discussing. Intramolecular forces, that's bonding. These are the forces within the molecules. These are the forces that attract the ions to each other. This is the single, double, and triple bonds of covalent. This is the electron C of metallic. So our different types of intramolecular was ionic, covalent nonpolar, covalent polar, and metallic. All of these are intramolecular forces. Okay, so what is holding these molecules together to itself? A change in an intramolecular force is a chemical change. So if I take hydrochloric acid and I add 431 kilojoules, I add so much energy that I actually separate these two atoms from each other, creating hydrogen gas and chlorine gas. That's a lot of energy, 431 kilojoules. So an addition of a large amount of energy breaks the intramolecular bonds and thereby forms new compounds. This is a chemical change. This is what we've always discussed as a chemical change, the formation of a new substance. An intermolecular force, what we call IMFs, this is the attractive force between molecules, between different molecules. I have a compound on the left and a compound on the right. What attracts these two to one another? They're not going to create a new compound. That'd be a chemical change. This is what holds them together as a solid or a liquid. That's what we're going to be discussing. Our intermolecular forces, a change in them is a physical change. So if I take the same amount of hydrochloric acid, but instead of adding 431 kilojoules, I only add 16 kilojoules. Well, now my liquid, hydrochloric acid, is now gaseous, hydrogen chloride. The addition of a small amount of energy overcomes, okay, and this is the correct verbiage I want you guys to use when we're discussing intermolecular forces. The amount of energy that overcomes the intermolecular forces that holds the molecules in a specific state. So right here, my compound was being held as a liquid. The molecules were being held near each other and sliding past one another, using all those properties you already know about the states. By adding 16 kilojoules, now these hydrogens and these chlorines that were bonded together, these now are still bonded to each other inside the compound, but we break what's holding one HCl to another HCl to another HCl. Breaking that is what creates my gas. So we're going to be focusing on states of matter, intermolecular forces, and the states of matter. The two we really want to focus here, because we're going to be using calculations with them somewhat, is delta H of fusion and delta H of vaporization. Fusion is going from a solid to a liquid. Vaporization is going from a liquid to a gas. And you might need to add the O-N on the word vaporization. It got cut off by the picture. So we can actually calculate the amount of energy required to make each one of these jumps. And we will do so. And we'll do it per mole, and we'll look at our chemical equations. So just because we write a chemical equation, keep that in mind, it doesn't necessarily mean a chemical reaction has occurred. This is a chemical equation representing a physical change. Okay, we have a liquid going to a gas. So we know that in order for a substance to go through a physical change of changing states, energy must be added or subtracted depending on which direction we're going around this circle. So starting with a solid going up to a gas, all of this would be the addition of energy. So we know that we have to add this energy. Now why? Because we must add energy to overcome the intermolecular forces. Here's that same verbiage, overcoming intermolecular forces that hold the molecules close to each other in a solid or a liquid. This is what a solid is, what a liquid is. It's these compounds that at that certain temperature, with the amount of kinetic energy that they currently have, are they able to overcome attractive forces between each of the individual molecules. So we have 3 types of intermolecular forces. Our first type, well, first off, I want to point out the fact that intermolecular forces are also called van der Waals forces. You'll see it rarely, but if you do, that is for IMFs. The first kind is London dispersion forces. Sometimes the London is taken off and we just talk about dispersion. These are between all covalent molecules, whether they're polar or nonpolar. Then we have dipole-dipole forces. Dipole-dipole are both between a dipole and another dipole, so it's between polar covalent molecules. The only thing that have dipoles are polar molecules. And then hydrogen bonding is only between the H of one molecule and the NO or F of another molecule. Hydrogen bonding is by far the strongest, but it's rare. It only happens between the 3 most electronegative elements, NO and F, and hydrogen. Okay, this attraction between the 2 creates hydrogen bonding. Hydrogen bonding is the strongest intermolecular force. It is horribly named. Hence why anytime that I write the word hydrogen bonding, I put the bonding in quotes. It's not a type of bond. It's a type of intermolecular force. Badly named long ago, hasn't changed. So let's look at London dispersion forces. London dispersion forces are created by momentary or an induced dipole. Just using this vocab, you should be able to figure out what this means. A momentary dipole is a dipole that only exists for a moment. It's happened by chance. An induced dipole is something that is actually induced. Think of induced labor. Okay, so something that has been created, brought upon by something else, some other stimulation. So a momentary or an instantaneous dipole is a better way to describe it as well. A momentary or an instantaneous dipole results from the constant motion of electrons. It just happens. Okay, these electrons are in constant random motion, and that random can end up with too many electrons on one end. So if we look at the picture right here, this would be a momentary dipole on one helium. Helium only has 2 protons, 2 electrons, and in this constant circling of the electrons, it happens that 2 electrons end up on one side. That would create a slight dipole. It's momentary. These electrons are going to continue moving and the dipole disappears. But this happens over and over and over again because it just happens randomly. So we have 2 here, and then another point, there might be 2 up here or 2 down here. That would each time create a slight dipole. So a momentary dipole. An induced dipole results from the electron pull or repulsion from a nearby ion or molecule. So this is induced. It's the electron pull or repulsion from a nearby ion or molecule. So if I start out with one helium that has a momentary dipole and another helium, with these 2 go near each other, well, this momentary dipole on this first helium actually creates an induced dipole on the next helium. The fact that there is 2 negatives on this side leaves some positive pull here. This positive pull here actually attracts the electrons on this normally perfectly neutral helium over onto one side, creating a weak attractive force between these. Remember when we talked about ideal gases, we said we just ignore the fact that intermolecular forces occur, makes our calculations easier, but they do occur. The problem is, remember, if they're going really fast and they have a lot of area to go around in, this is very rare to happen, and when it does, it's not very strong. But you take helium and you start lowering the temperature, lowering their kinetic energy. They're going slower and slower and slower. And when this helium passes this helium, all of a sudden this attractive force isn't just automatically overcome. This actually brings these 2 closer together. So we keep decreasing the temperature. This happens more and more and more until we have a liquid of helium. Now this is about negative 100 and something degrees, but there is such a thing as liquid helium. You've lowered the kinetic energy so much so that these don't have enough energy to overcome the intermolecular forces of attraction between them. Now they're stuck in a liquid and they're sliding past one another. You continue to lower their speed. You continue to lower their temperature, taking away energy. And now they're not even sliding past one another. Now they're stuck in a rigid structure, which is a solid. There is such a thing as solid helium. It requires ridiculously low temperatures, but this is how it can occur. From these induced and these momentary dipoles, it will create a slight attraction between these. And if they're going slow enough, that slight attraction will eventually hold them into place. That is what a solid is. They don't have enough energy to overcome those slight attractions between all the molecules, so they're held in a rigid structure. So, the strength of dispersion forces depends on the total number of electrons. Well, the more electrons there are, the more likelihood this is going to happen. The more momentary dipoles there are, the more attractions there are. So the bigger and bigger the molecule, the more electrons there are, the more of this is going to happen. These London dispersion forces actually determine most of the properties of substances, such as their boiling point or their freezing point. Both of those are based off of how much they're attracted to one another, and usually London dispersion force is the thing we're talking about, because London dispersion forces apply to all covalent compounds, no matter what. Except for hydrogen bonds, we'll end up changing these. So whenever we talk about something that has a hydrogen bond like water, water is really small with very few electrons compared to the other ones. But water has a huge boiling point compared to its size. That's because of these hydrogen bonds. So we're going to have to take hydrogen bonds into account later on. So these do act between all atoms and molecules. And these are the only attractive forces between nonpolar molecules and other nonpolar molecules or between noble gases. This is the only possible thing that can actually make them go into a solid or a liquid. Next we have dipole-dipole forces. Now these should be pretty logical. It's between the dipole on one and the dipole on another, because it's an intermolecular force, so it's between the molecules. So it's the attractive force between a dipole on one molecule and the dipole on another. This acts between all polar molecules. If you can identify that something is polar, you know that it has dipole-dipole between each of its molecules. So this dipole-dipole is usually stronger than London dispersion unless the London dispersion molecule has a ton of electrons. Now, every molecule has London dispersion, so we would say that if something is polar, then it has London dispersion and dipole-dipole intermolecular forces. Well, everything has London dispersion no matter what. So visibly, we have the positive end and the negative end on each of these molecules. The positive end of one and the negative end of another will be attracted to one another. This continually happens. They don't have a lot of energy to overcome this attraction between them. Now they're stuck sliding past one another and they're liquid. This continues to happen. They slow down even further. They're colder and colder. Now they can no longer even slide past one another. That is a solid. This intermolecular force now holds them in a rigid structure. Now we're a solid. Okay. Hydrogen bonding, the last one. Once again, it is inaccurately named. Try and keep those quotes in your head when you think of hydrogen bonding. It is not a type of bonding, it's a type of intermolecular force. This is the attractive force between the polar hydrogen on one molecule and the polar NO or F on another. This only acts between polar molecules with a hydrogen and a NO or F. It's very strong. It has a lot of things that change the properties, but it's very rare. Okay. Of course, the most common one we talk about with it is when we talk about water. The hydrogen bonding of water is what makes water so unique. It's what changes its boiling point, its freezing point, its interactions with everything else. Okay, water has London dispersion because it's a compound, voila. It has dipole-dipole because it's polar, and it has hydrogen bonding because it has H's and O's. So it has all of these intermolecular forces that hold it together very strongly, which creates this rigidity. At the bottom, I want you to fill in this flowchart using these words from this bank here. Make sure you can differentiate where these two are interacting with one another, these intra and these intermolecular forces. This table right here will be your lifeline for this unit. Just like your table of your molecular geometries and electron geometries, that was your basic resource for the last chapter, this one is going to be very important here. Right here in my very first, I have metallic, ionic, network, and molecular. These are my types of intramolecular forces. Intramolecular. So first we look at what is our intramolecular forces. We look at what composes that intramolecular bonding. We look at the compounds. We can look at the types of intermolecular forces that play a role. So this is what makes them solid, liquids, and gases. That's what, when we're talking about intermolecular forces, that's really what we're talking about. What is it that's making them into solids, liquids, and gases? Okay. And then when we're talking about properties, this will be crucial for your lab this week. We're going to be comparing types of bonds. Well, our types of bonds have all these different types of properties. We also have different properties based off if it's polar or nonpolar. So make sure you read through this and find some very interesting information here and how you would apply it. At the bottom, I have a flow chart for intermolecular forces for you. Try and differentiate all these different concepts. And at the top of the next page, I have a flow chart for how are you going to compare boiling points, freezing points, and lattice energies. Okay, so when we're talking about what's holding them in their states of matter, those are the three things that we really consider. Boiling points, freezing points, lattice energies, what's holding these things together. Okay, now if you're going to be comparing things, you need to be comparing if they're ionic or covalent, if they're polar or nonpolar. This flow chart will be crucial for you when you're going through OWL. OWL specifically will be talking about comparing these things. Intermolecular forces, that's the biggest thing we focus on, is if you're able to just be given two compounds and say which one would have a higher boiling point because it has more intermolecular forces. So read through that, highlight interesting information. This table at the bottom, I'll go through a couple of these very quickly with you, but most of them are questions about state of matter, like what's held in a rigid structure. These are things you should already know coming in here. So if you struggle with any of these questions, get help immediately. I'm going to go over all these questions again with you on Wednesday when you're back in class. So the first question, circle the compound or compounds with hydrogen bonding. Okay, NH3, it has an N, it has an H, it's polar. To fill out this table, I'm not giving you specific words. I want you to be able to just differentiate between them. So kinetic energy, well, who has the most kinetic energy must be a gas. So you'd say highest. Solids have the lowest, and you really don't need to put anything for liquid because it's pretty logical. If this is highest, that's lowest, voila. Okay. For amount of order, you can also think about it as amount of disorder or rigidity. Okay, how much is something being held rigidly versus completely free-flowing? Okay, obviously, highest amount of order in a solid, lowest in a gas. So go through and just use comparative words to identify each of these. If you struggle with any of these questions, answer them in pencil so we can go back and change them if you need to later. All right, this diagram right here, we're going to be working with these a lot in this unit. For now, I just want to add a couple concepts to it. First of all, whenever you have this plateau, right here and here, if you notice, energy is being added, but my temperature stops going up. If I'm adding energy, why on earth is my temperature not going up? Well, temperature is the average kinetic energy. So from here, while my temperature is going up, that means this added energy is just increasing the speed of these molecules. But right here, it's not increasing the speed. The added energy is being used to overcome the intermolecular forces. That's why we don't see an increase in temperature right here. Temperature is staying constant because there is no increase in the speed of the molecules. This added energy is now being used to actually overcome and separate each of these molecules from each other. So if I'm going from a solid to a liquid, I'm separating them enough so they can flow past one another. The same thing happens here. So I'm just going to color it the same color, where once again, this now added energy is no longer increasing the speed. Once again, my added energy is now separating these liquid atoms into gaseous atoms. They're not being held by intermolecular forces at all anymore. Now they're able to freely go about as they will.